Hi, my name is Brian Caffo, and this is the lecture on residuals and residual variation in the regression class for the Coursera Data Science track. This class is co-taught with my collaborators Jeff Leake and Roger Peng, and we're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so we've talked about our regression model fit, but of course the model doesn't fit the data perfectly, or usually it doesn't fit the data perfectly. And we've set up our model where we're talking about additive IID. I should have IID there. Errors that are normal 0 sigma squared. So the observed outcome at data for data point I is yi, and it has an associated predictor value xi. The predicted outcome we'll call yi hat. So I don't know, you can't see it terribly well. Let me get rid of all the markup real quick and then do it again. But that little hat right there, that's our predicted value, and that's nothing other than take our estimated slope and our estimated, our estimated intercept and our estimated slope, and then multiply it times that x value. So that is the value at the regression line, right? That's yi hat, and the actual data point, that's yi. And remember, our least squares criteria minimizes the sum of the squared vertical distances between the observed data point and the fitted lines. Now, if we actually had beta naught and beta 1, and our model was true, right? Then if we were to subtract yi minus yi hat, we would actually get the actual real error. Of course, we don't have beta naught plus beta 1. We have the estimated values. So we might kind of estimate the error at that point. We might take yi minus yi hat and get something that we call ei. Right? Now notice ei is not epsilon I, right? Epsilon I is the true error that we don't get to know because we don't, and also we don't even know that the model is correct. Ei is nothing other than that distance itself. So you can think of the least squares as minimizing the sum of the squared residuals. These guys are called residuals. The least squares minimizes the sum of the squared residuals, where the minimization has some constraints on the linear form. You can sort of think of the EIs as sort of estimates of the errors at that particular data point. So let's talk about a couple things about the residuals. First of all, their expected value is 0. And if an intercept term is included, the sum of the residuals is 0. So that means they can't possibly be independent, right? Because if you know n minus 1 of them, then you know the nth, right? Because they all have to add up to 0. And in fact, as we proceed in linear models, if you fit p terms in your regression equation, then if you know p n minus p of the residuals, then you know the remaining p residuals. And that's because this latter fact that if a variable x is included in the model, then the sum of the residuals times x is also equal to 0. And of course, this statement right here is equivalent to this statement in the case when x is 1, which is the residual case. Okay. So residuals are useful for a lot of things. They're good at investigating poor model fit. They factor into, or they're exactly yield our variance estimate. And so residuals are kind of very important things. So positive residuals are above the line, negative residuals are below. And one way we can think of residuals is they're sort of the outcome y. I'm going through this statement right here. The residuals are the outcome y with the linear association of the predictor x removed. So you might think of it as y adjusted for x is the phrase that's often used. But what it means is adjusted for the linear association with the predictor x, right? If there's a nonlinear association, we haven't gotten rid of that. So often when we talk about regression models, what we're differentiating between is residual variation, which is variation that's left after removing the predictor, from systematic variation, which is the variation that's sort of explained by the regression model. So if there's perfect relationship between the y's and the x's, then there is no residual variation. If beta 1 is 0, if it's just a horizontal line and only the intercept, then there's, you know, all residual variation and no regression relationship. And residual plots can highlight, you know, this latter fact. Residual plots can sort of focus in on aspects of poor model fit in a way that the scatter plot can't, and then when you go to higher dimensions with more variables, then you don't even have the equivalent version of a scatter plot. Okay. So let's, you know, create our residuals for our data set that we've been working with. So we're going to do data diamond. This is the diamond data set where we have carats were the predictor and diamond price and Singapore dollars were the outcome. So here I've just defined my y and my x because I don't want to have to keep typing data diamond, or I don't have to type in the data set when I fit LM. So my fit is just LMY tilde x. And you can grab your residuals by just doing resid of that variable that you assign the output of LM to. And you can get your predicted responses at your fitted x's by just using the predict function. And then just to show you that your residuals are exactly the difference between your observed and fitted values, let me just take here my residuals and subtract off the difference between the observed and the fitted values, and then I'll take the absolute value of those and look at the largest difference between my residuals, and you see that it's 10 to the minus 13. It's only at numerical precision, so, you know, suggesting that those are exactly the same. And then in fact, let's calculate it here directly, where we, instead of putting in getting the y hats from the predict function, let's put it in directly, where we take the first coefficient, this is beta naught hat, and the second coefficient, which is beta 1 hat, right? I guess R likes to count from 1, whereas, I don't know, computer scientists tend to like to count from 0, so 1 versus 2 as opposed to 0 versus 1, and then multiplied times x, my x value is right here, so this is going to, this right there is going to give me my yi hats, okay, and then look at, gives you the same exact number when you take the difference between those and the residuals that R puts out. So we know exactly where those numbers are coming from. We can calculate them directly. So here's the residuals. The residuals are the signed length of the red lines in this plot. So we could kind of, it's not rotating this plot. It's sort of rotating plot in a way that the vertical distances are preserved, and we could plot the residuals versus x. And that's actually a very good thing to do. Here's the plot, mass and carats versus the residuals. And that's a good thing to do because the reason is, you know, especially when there's a good fit, you know, there's all this kind of blank space right there and right there to hide things. So, so what sorts of things do you want to look for in your residual plot? You want to look for any pattern. Any evidence of a pattern means that there's some sort of systematic thing that you've omitted in the model that you maybe should have. So here's an example where I'm going to simulate some data and show you a residual plot. So here I generated my x's are just a bunch of random uniform numbers between -3 and +3, and y is, it is this line, it's the y = x line, but then it also has this other part with sine x. Okay, so it's not just y = x. It's not, and then I add some normal error. Okay, and here's my scatter plot, and here's my fitted regression line, and you can see, you know, in this plot you can sort of see what's going on. You can kind of tell that there's some sort of relationship there that we're missing, that sine x part. But look at what happens when you do it on the residual plot, you know, and you can see it. You can see it much more clearly, right? You can see it exactly right there. Okay, so that sort of pattern in your residual plot would certainly be something that screamed out at you. This something systematic like that. Well, I tried to create an example where you couldn't see anything from residual plot, but it was, or from the scatter plot, but it was obviously an apparent. And so what I was going to talk about here is heteroscedasticity, and this is a case where our model is not right because the variance isn't constant as a function of x. So here I generated my x's as random uniforms, my y's were x's, so my linear regression relationship holds with an identity slope and zero intercept. But notice here my standard deviation of my normal is, let me just get it. My standard deviation of my normal actually depends on x, right? So that's called heteroscedasticity. So we have, you know, one of the assumptions of our model is that sigma was constant. So again, let's plot it. And so if you plot it, you know, here, look, you know, it looks like a perfect regression model fit with nothing wrong. But you know, if you do the residual fit, you can see the heteroscedasticity very clearly. So you know, you don't often, you know, that's the variance of the response increasing. See the variance increasing for a given value of x. And you don't kind of encounter data like that very often, but it goes to show you the point that residual plots can highlight patterns that are often missed when you do a scatter plot. Plus, not to mention when you go up to higher number of variables, you can't do a scatter plot. You have too many variables. Okay, so there's just two examples that I simulated really quickly. So the residuals are useful for estimating residual variation, right? So the residual variation is, remember in our model right here, our residual variation was that guy sigma squared, right? That's the variance of the y's and also the variances of the epsilons. So the ML estimate works out to be this guy, the average squared residual. But most people for regression use that guy, which is not the average, but n-2. So you could either think of this as, well, what's the difference between n-2 and n between friends? You know, the ratio for a large n, n over n-2 is really small, so, you know, forget about it. But if you're a stickler for the details, you might want to wonder exactly why is it we don't use the MLE. And it turns out that the MLE is biased in this case, in that if you want your estimate to be unbiased, its expected value to actually equal sigma squared, then you need to subtract off 2 there, 1 degree of freedom for the intercept and 1 degree of freedom for the slope. And because we had to estimate those 2 parameters, they get subtracted out, is the way to think of it. So that's why people do that for purposes of unbiasedness. But again, if you don't want to concern yourself with that level of detail, it's no different than dividing by the n-1 when you take the ordinary standard deviation in that. You know, that's just what people do. But the technical reason is for unbiasedness. So let's get our variance estimate from our data. Okay, so we have, there's repeating statements we've already done. Here we are fitting our model. But remember, we actually showed you how to fit the model without doing LM. Obviously, you're going to do LM when you do it in practice, but now you also know how to do it without doing LM. If you want to, the function summary really gives you a lot of information about the fitted model. So summary is great, but summary creates a list, and the specific element of the list, sigma, is the residual variation. It expressed as a standard deviation, and in this case that works out to be 31.84. So what we could do, just to show you that it's the same, is we could get the residuals and square them, and then divide the sum by n-2, and that will give us sigma hat squared, and we want to look at sigma, so we can do square root of that to look at sigma. You see it works out to be the same number. So it's interesting that you can kind of summarize variation in a kind of clever way. So let's look here, you know, n-1 times the sample standard deviation is this guy right here. So that kind of would represent just sort of total variation in the y's. Variation in the y's disregarding everything except maybe its mean. Okay? And then, so let's look at that and then add and subtract y hat. And then if we expand out the square and distribute the sum along our expanded square, we get that guy. But then let's take this this term right here, yi minus yi hat, and this term right here, and just look at them really quickly. First of all, notice that yi minus yi hat, let's add and subtract, let's see, not add and subtract anything. Let's just remind ourselves that yi hat is beta naught hat plus beta 1 hat xi, and so that's what we're plugging in right here. But also remember the definition of beta naught hat is that right there. Okay, so I'm gonna get rid of some of those annotations so we can see, and then just get so collect all these terms, and you wind up with that right there. It works out to be yi minus y bar minus beta 1 hat xi minus x bar. So which is nifty little simplification. And then doing the same sort of thing for yi minus y bar, you wind up with that. That works out to be beta 1 hat xi minus x bar. So take this guy and then plug these two things in with our simplifications, and you wind up with this expression right here, which you can then distribute the sum across and get that guy minus that guy right there. And of course you can churn through the details, but then you wind up with the sum of the x deviations plus the sum of the x deviation. I'm sorry, the sum beta 1 squared times the sum of the x deviations minus beta 1 squared times the sum of the x deviations squared. And of course these are both the same thing, so they equal 0. So, and I have used throughout, if I've used the sum of xi minus x bar just is 0, and sum of yi minus y bar is 0. So if you're having trouble recreating these details, make sure you remember those facts. Okay, so the end result, our total variation is equal to our residual variation plus this model variation. So that's expressed as total variation is residual variation plus regression variation. And just to remind us where this equation is coming from, remember we showed that part goes to 0. That part goes to 0, and so we have those two guys right there. Just okay. And so what we could do is we could take this guy as the denominator and put it down there, and put this guy as the numerator. And because this guy is a bunch of squared terms that has to be added to another bunch of squared terms to total up to that guy, we know that this has to be less than that one. So we can describe this number as the percent of the total variation explained by this, the model variation, not the residual variation. Or it's equivalently, we could describe it as 1 minus the percent of the total variation that's left over, right? This guy right here would be the percent of the total variation that's just expressed in the residual variation, okay? And so anyway, the percent of the variation, total variation that's explained by the model is described as r squared. Oh, there you go. So-called r squared. So very briefly, I want to talk about what's the relationship between r squared and r, which is the empirical correlation between the x's and the y's. Recall that yi minus y bar, yi hat minus y bar from 2 slides ago is equal to this guy. so if we were to plug that into here, right, you can reduce that expression to this right here, which is exactly the correlation squared, where to see that, it's not immediately obvious when you look at that why that's the case, but remember you have to plug beta 1 hat, which was the correlation times the ratio of the standard deviations, plug that back into there and you'll see that's the case. So the long and short of it is, if we define R as the correlation between X and Y and R squared as the percentage of the total variation explained by the model, R squared is literally R squared. Okay, and that's maybe where it gets its name. Okay, so just briefly some facts about R squared. It's the percentage of variation explained by the regression model. I'm missing an M there. I'll fix that in the repository. R squared has to be between 0 and 1. We've shown that. R squared is the sample correlation squared. We've shown that. R squared is a misleading summary of model fit. For example, you can just delete data and inflate R squared. If you have a bunch of data and you chop out all the middle data points, then that can give you an inflated R squared. And then for later, if we add terms to a regression model, it automatically increases R squared, whether or not those examples are, those data points or those variables are actually useful to include. Just add random noise to a model as variables and it increases R squared. And then here's an example. Anscombe came up with a great collection of data sets to illustrate some issues with R squared. And so they basically had, in the data set, they have basically the same mean for the X and Y's, about the same correlation for each data set, and the slope estimate is about the same. But when you actually plot the data, here's data, you can just do it in R by saying data Anscombe and example Anscombe, and you see very, very different regression relationships. One is and these all have the same R squared. This one has kind of like what we would think of when we think of a regression relationship. This is clearly a no variance kind of quadratic that you shouldn't fit a line to. Here's one that's sort of a no variance line with a single outlier, and here's an instance where you have, all of your data is at one single X value and one data point up at a large X value. All of these wind up with the same R squared, so it shows you that even reducing simple data sets down to that single number isn't necessarily the best thing to do.